Can they read this? I know, and I made them be gone. Okay. Recap real quick. Okay, so with entropy, everybody, so entropy, as we highlighted, is a form of energy. Its typical units are joules per Kelvin. It's different than enthalpy. But when we talk about total energy overall, we're going to find actually it's a connection between the both of them. So we kind of have a tongue twister this unit, and we'll be often looking at the enthalpy and entropy of a system together. So they're connected, but they're not the same thing. Besides that, they're both a type of energy. Okay? So as we see in our picture here, right, that the more disordered a system is, this one would have a higher entropy than when it's all together. Okay? So that's kind of like with our eyes, you can often look at the entropy in that way. Going down to the molecular level, though, we have to think about the movement of the molecules. Now, I don't know if you can read this all the way, but next time your room is messy, you can blame entropy. Entropy is the reason that our rooms get messy because here's a key difference between our delta H and our delta S. Delta H is what again?
Change in temperature.
Not direct change in temperature. Heat energy, which is related to temperature, right? Heat energy is always conserved. Any heat I lose, something else takes in, right? It doesn't go away. It doesn't come from nothing. It just transfers and moves throughout the universe, right? So this is always what we say conserved energy, right? It's not created. It's not destroyed. Delta S is not that way. When you look at now you got to think of it as the whole net entropy of the universe, okay? The second law of thermodynamics states that the entropy of the universe is always increasing. So that's in terms of heat energy. Yeah, good clarification though, Ian. So that's the difference is entropy as a unit of energy actually is always increasing, which pretty much tells us that the universe is constantly going to a place of disorder.
Yeah, it's always expanding.
It's expanding, everything gets more chaotic naturally. Now that doesn't mean things can't get more organized. So that's where they're going to come into play, is both of them are there. The thing is things can go down in entropy individually. Okay, this doesn't mean everything always goes up. But as an overall net of the entire universe, it is always going up. Okay? Now, in order for entropy to go down, some sort of work in other forms, typically heat or heat energy, has to be used to make it go the other way. The natural way is to not get more organized. Same thing with your room. You can keep it clean, but it takes more work to keep it clean than it does for it just to naturally explode, right? I feel like that's what happens to my desk every day. It starts out clean, and then by the end of the day, entropy took over. Skytime wasn't too busy today, so I kind of reset it. You didn't see it during Skytime. Okay, so when we look at an equation, there's two factors, two main things you want to focus on, okay? So I'm going to color them in different colors. So the first one, this one plays the bigger role, is the states of the substances. And we'll dive a little bit more into this. But the first thing you want to look at is what are the states of the substances? Are they changing from a liquid to a gas? In this case, they're all staying the same. And so that we wouldn't consider for entropy. But it is what you always want to look at because that would play a very big role in the entropy of a system. Okay, switching colors, the second thing we look for is just amounts from reactants to products. So in this reaction, I have 3 moles of reactant total, and it's turning into just 2 moles. Having less things, oh yeah, go ahead, Garrett.
Does the entropy correlate to the pressure or something? Or no?
Changes in pressure would change entropy, yes. Is that kind of what you're saying? Like, is there a connection? There is, yeah. So would you say having 3 or 2 things is more organized? 2. Less is more organized. So this we would say has an overall negative change in entropy. The entropy has decreased from the reactants to the products because they're all the same state, but you now have less things. Right? If you declutter your home, it's more organized.
What would be the difference if it changed states? Like, would that increase enthalpy?
So let's say, to give an example of what you're saying, so hypothetically, let's say instead of a gas, if this turned to a solid, then definitely entropy goes down.
Okay.
Because it's coming together.
Yeah. And we'll look at some more examples, but good question, Solomar. Any other questions so far on that? Okay, let's look at the molecule. So this, by the way, if you want to draw an arrow, is this on your paper? I guess it's not even on your paper. This picture right here is the same diagram of the equation we just saw. So this is just the view of it, right? So you can see once again, we had 3 as reactants. Once they bonded, now we only have 2. So in general, the formation of a new bond decreases the forms of what we call the degrees of freedom, which is how freely the molecule can move. The more it's bonded, the less degrees of freedom it has, which is directly linked to entropy. So that's another way you can think about entropy is the degrees of freedom. The more molecules can move, and I'll show you a dance here in a second to help you remember it, okay, the less entropy it's going to have, okay? All right, everyone okay here if I go to the next one?
Does chemistry just more always equals less, basically?
More always equals less?
Because you just said more, what did you say, more atoms, less, it moves less freely, right?
If it has more bonds, then it moves less freely.
So yeah, like, more is less.
Yeah, I guess so. Okay, so when we're talking about degrees of freedom and movement of molecules, okay, there's 3 different ways a molecule can move. We have translational motion, we have vibrational motion, and rotational motion. The more of these a molecule has, the more degrees of freedom, aka the more entropy. All right, so with our 3, I just realized that's the one downside with filming on my iPad. They don't get to see the dance, so one of you guys will have to show it to them. Now, B6 convinced me that if you do this dance at prom this weekend and film it and show it to me,
No way.
I'll give you 10 smiley faces.
Can you?
And if you can convince the rest of your prom group to do it with you, then you can get 20. Now, if you aren't going to prom, you just have to do it in some public place.
No, you gotta go to Salt Lake City.
And then you can get this my face as well.
My brother's wedding reception is during prom, so that one
That'd be a perfect place to do it, yes. But you have to bring back proof because I want to see it. Okay.
Bring the people that you.
So that's not the same issue. Having to do it. That's great. Okay, up here, everybody. So with these type of movements, ready? I'm going to model for you. Here's how the dance goes. So I'm going to pretend, for example's sake, that I'm a water molecule. Okay? So pretend.
Do you have to explain this to your phone group?
Guys,
see is video
just
of you doing
visualize that I'm a water.
But if you want to be really cool, then yes. Okay, this is my head's like oxygen, and my hands are hydrogen. So see my bent shape.
Oh my gosh, it's bent.
Right?
No
Okay.
way.
So first type of movement is translational. Translational is the actual movement of the molecule moving
up
through
and
space.
down.
So up, down, left, right. This is translational movement of the molecule. Got it? Okay. All right. Now, vibrational is often confused because we think of like how our phone vibrates. But when we talk about vibrational in terms of a bond, it's how the bonds can move. So vibrational can happen in different ways. So here's the bond, right? From here to here. So they can move like this. That's a vibration. They can move like this. That's a vibration. Or they can move like this. Okay, so that's what we mean by vibrational, right? Is bending, symmetric stretching, or asymmetric stretching. Okay? All right, and then rotational is the molecule spinning, right? So this right here is rotational.
I'm gonna get dizzy.
So if you are a molecule that has all 3 forms, so this is the dance, we're gonna do it all together. All 3 forms of them at the same time, right? So you're gonna have translational, vibrational, and rotational. You can pick your mode of vibrational that you want. But there's some freedom there. Oh, I got this. You can't spin like a Something happens to your ears. Okay. Does that make sense what those words mean now?
Yeah.
What? Can you do it as a class right now? You want to practice?
Will we get kicked out of the AP test if we start doing this?
Yeah, maybe wait till after. And then it becomes like this whole
Use it to remember. Use it to remember. All the students.
Okay. So let's think about this one. I'm sorry, I don't know what happened with some of the image. I had a good practice problem, and then some of my images disappeared. But let's take a look at, I think this little paragraph is there. The image just isn't. So as we think about these degrees of freedom, once again, the more degrees of freedom something has, the more disordered it is, which you can see, right? If everybody at prom was doing all three of those at once, like that's a pretty disordered system, right? Versus if you're all just like doing vibrational, right? Which doesn't have, you're just spinning, right? Less and less. So if something is a solid, its only type of energy would be vibrational, right? Things in solid form, they can't translate. They're not moving forward and back, up or down. They're not rotating. The bonds are just vibrating. When I move from a solid to a liquid, we increase and we now have the ability to do translational movement, right? Water molecules can move past each other. There's even an argument for some rotation as well, right? That in water, the molecules can rotate. It's just probably not freely, right? Because you're like side by side with each other in water, right? But it's not unable to do rotational. But then, of course, as a gas, now you have all three forms of movement because you're way spread out, plenty of space to move. Questions on what degrees of freedom? It's kind of a fancy phrase, but hopefully that kind of makes sense of like what it represents once again, right? Junior high students at dances have very low degrees of freedom because they stand against a wall, right? Most of the time. I don't know. I haven't been to a junior high dance since ever. But. Okay. All right. This summarizes the three things we talked about, and then we'll try a practice problem. So once again, the first thing you want to identify is the state of the substance. Is it a solid, is it a liquid, or is it a gas? That trumps amount. Okay, being a gas has way more disorder than having 3 molecules of solid. Okay? So always look at states first because that will have a bigger impact. Then, if states are the same, then you can look at the number of molecules present. Once again, having more molecules provides more. Now, one type of state we didn't directly address is the process of going from a solid to aqueous. Which one would have more degrees of freedom? Something as a solid or as an aqueous form? Good, yeah. So that's also like a state of matter outside of solid and liquid and gas to pay attention to if it has that little AQ next to it. Okay, let's try this one together, and then I'll have you try the next one for smiley faces. So this is very similar to what your homework looks like tonight of just identifying positive or negative. Is entropy increasing or decreasing? So looking at A, I would first identify, water's a liquid, and it's going to a gas, right? So I'm going to highlight these here, which means my degrees of freedom are increasing, so entropy is positive. So an overall positive change in entropy.
Sick.
Number 2, we're going from aqueous. So once again, notice I don't even pay attention to amounts. I just focus on states first. Right? We're going from aqueous to solid, which means entropy is definitely going down. Right? It's getting more organized. They're losing degrees of freedom as it becomes a solid. And then the last one here goes from a solid and a gas to just a solid, which means overall it's lost entropy. Yeah. And you could also, this one even supports the fact of the amounts, right? That this one goes from 7 down to 2, right? So you have way less molecules there as well.
Are you able to just look at the what state it's in?
A lot of the times, yes. A lot of times, if the states don't change, then look at the amounts. But a lot of times the states will help you identify it. All right, any other before I have you try the next 3 as a table? Okay, flip the page and try this one as your table for 3 smiley faces, and then we'll check it. Oh no, he left us test.
Oh
What's
yeah.
he doing? That's so funny. Give me a pencil drop when you're done. Yeah, key difference. Drop, not throw. Random 5th chair here. B5 has 37 students. Kind of annoying.
Yeah, that's kind of.
Okay, everybody ready? You guys ready to check it? Everybody ready? Okay, here's what I want you to do, and then we'll confirm if we're right or not. So you're going to show me your sign by going plus or minus. So show me for the first one. Is entropy increasing or decreasing? Show me your thoughts. Ready, go. Good, you're all showing me plus. Let's see, Evan, will you give us just a quick why? Why does it go up? Perfect, good observation. Have a smiley face if you said plus. Evan, have a bonus for helping us out. Okay, show me for E. Plus or minus, show me with your hands or fingers. What's happening there with our entropy? Very good. Just have a smiley face. You all said it's going down. And Dylan, can you tell us why it's negative for E real quick? Perfect. Yep. Less things, less chances of movement. If you draw the structures of those, C6H6 is so much bigger and has a much harder time like rotating and things like that as well. So good. Have a bonus smiley face for that. And show me F. What do we say for F? Is it going up or down? Very good. Have a smiley face for your plus sign. Good. Lily, and can you give us a quick why?
So since it's a solid and gas versus solid and gas, it's just because there's more products.
Perfect. Good, right? We get that a little bit more, not many more, but a little bit more product, which once again is going to give them more freedom to move. So
There's the difference with like the 3H2 and 3H12. Would that ever be a big thing? Like the one
Size of
So typically the formation of a bond decreases your degrees of freedom. But it's kind of tricky because some bonds are forming but other bonds are breaking, right? So like if you were just focused on comparing like this guy to this guy, I would assume that this one has more entropy. Smaller things have more freedom to move and stuff. But, yep. So now I didn't address it because we haven't seen one because it's not super common. But you can have reactions where the entropy doesn't change, and it actually is, the change in entropy is 0. So that is possible, right? If all the states are the same and you have the same number of moles on both sides, it's not wrong to say that there is no entropy change. But once again, it's pretty rare. Yeah.
Yeah, that was my question.
Yeah, it's pretty rare. So, okay. Yeah.
So does electronegativity have like a big effect on the entropy?
Somewhat when you get really deep because of how electronegativity affects polarity, and polarity would affect degrees of freedom, right? Because if something is polar, they're going to be attracted to each other stronger, which limits their motion versus, so like, yes.
Okay.
Not like in an easy way to say how it's connected, but there's a connection there.
Okay.
Yeah, good connection. Have a smiley face for that, Caleb. Okay, I'm going to put a question up on the board. It's a practice AP question. It's not in your packet, it's just on here. I don't want you to look at anyone else. Put up your blinders. This one I want you to try all on your own, and then I'll have you respond with A, B, C, or D. Okay, but don't look at anyone. Don't show me the answer yet until I ask for it. Okay, the question says, and then I'll scroll down, it says, of the following reactions, which involves the largest decrease in entropy? Okay? So take a look at those reactions. You're looking for the one that has the largest decrease in entropy. If you're ready to answer, tap your head. If you're still thinking, don't tap your head. All right, I'll give you 20 more seconds. I gotta get new batteries for my timer. I'm having to count in my head. Yes.
Oh.
It's
What
one of those
batteries does
things.
it take?
I think AAA.
I will donate.
Oh, that would be kind of you. I think I might have some buried in the lab somewhere, but it's just one of those things. I have batteries at home. I just
Forget.
don't remember till I'm here, you know?
Feel that.
Okay, everybody ready?
Yeah.
Okay, to make it easy, I was going to show you sign language, but we'll just do this and number them 1, 2, 3, 4, 5.
Whoa.
Okay, so on the count of 3, you're going to show me on your fingers what you picked. Everyone understand? Okay, 3, 2, 1, answer.
She said I'm counting 3 when she started.
I guess it was still 3 in one direction, Daniel. Okay, hold them steady. Don't move. Don't change. Don't be influenced by others. Stand strong on your own, even if you're wrong. Zach, you're confusing me. Okay, I think so the answer is E, or the last one. So good job. Any questions? So this is, once again, kind of an example. This is from an AP test of how it can be asked in that way. But
Dang, they should ask these questions in the AP test.
there will be one.
Oh, dang.
Yeah. Probably just one, but there will be one. So no, it's the same as
It says on
the
the
rest,
front, it says
but-
7 to 9%.
when I looked at like the most recent one, I think I found, yeah, typically like just one
What's the most?
in terms of just identifying entropy. But still, 1 point is 1 point. Okay, our last thing we're gonna look at today is how we could actually mathematically calculate an actual value of entropy. Now this calculation in this equation is on your formula sheet, so you don't have to memorize it, we just need to know how to use it. Okay, so the equation is that to find the overall change in entropy for a reaction, it's going to be equal to, now this equation, I hope, has a little bit of deja vu feel, because it's very similar to something we've done before. So if it does, that's a good sign. If it doesn't, that's okay, we're going to have a month to review. But the equation is, we're going to take, do you remember what this symbol means? So its name is sigma. It stands for the sum of adding them up. Okay, so we need to add up the sum of all of the entropies of the products minus, I don't have a guess what I'm going to minus it?
The reactant.
Yeah, the entropy of the reactants. So this is on your formula sheet, and it's right next to the equation we did with delta H. So, okay, everybody have that written down, and we'll try a problem together. Now, there's going to be a big context clue in the problem of when you need to use this equation. The big context clue is a table of the entropies of your reactants and products. Because this is not something you would just know, I mean, maybe, but like you're not expected to just know, and it's found through experimental means. So this has to be given in the problem if I'm going to use this equation. And if I see that it's given, then I should know, oh, well, I'm probably going to use that equation. So I have that table, I have my reaction, so we're just going to set up the products minus the reactants. Now I'm going to use different colors here on mine to indicate where I'm getting numbers from, so if you want to highlight them as well to help you remember where they came from. So I need to start with the product side, so products I'm going to write in purple. Now keep in mind there's 2 NH3s, so I need to do 2 times the value of NH3, which is 192.5. So you got to take into account how many you have and then times it by the amount. Okay, so that's my products right here. So now I'm going to minus my reactants. I'm putting a bracket just because I have 2 reactants, so I want to add those together. So I'm going to switch here to a different color. So for my reactant, I have N2. There's only one of those, so it would just be 191.5 is its value. And then plus, we have 3 H2s. So 3 times 130.6. And then let your calculator do the work. Questions on any of my numbers or where I got something from? I can't remember. I think the answer is like -198 or something. Anyone type it in yet?
I don't know.
I'm just trying to remember from last period. Thank you. -198.3. Any thoughts on the unit of my answer here?
Joules? Or joules of mole?
Close? The mole part cancels out, but good observation, Ian. So the moles up here get canceled by timesing them by the amounts, so it ends up just being joules per Kelvin. Now, it's always good logic to do a quick check and say, is the sign of this logical? Without even solving this, does it make sense that the entropy is going down?
Yeah.
Yeah, right? So it's always a good quick check because you might be able to catch yourself if you made a mistake somewhere in your math, if you get at least the wrong sign of it. So
Why did the moles get canceled out?
because right here, like where we did the 3, so that was 3 moles times the joules per mole Kelvin. So the moles go away. Yeah, good question though. Any others before I have you try the last one for one more smiley? Okay, try this one. When your table's ready, raise your hand and I'll come check you off. Ready, go.
Oh, yeah, I saw the C and the CH.
Just kidding.
Exactly. I love that it's 2 5. You are fast.
I know.
I don't.
I charged my I charged my calculator.
Yes, it is.
I charged my calculator and so so once I set up my backup
More than you are like. We don't use addition very often, so the main rule I always think of is multiplication. The addition rule, since all of these go to tens. I don't know.
How good is more important than the other? I put my calculator on my sport.
Got it? Good, how's my face? What did we get over here?
I did it, guys.
Good job, how's my face? Yes, good, how's my face? What did we get over here?
I was like, wait a minute. I got a different number.
Your work, if you didn't up there, is not going to be
I use every single. I had exactly that.
Halfway charged. Oh, now it's back to 1.
Okay, I don't know if I checked you guys out.
Wait, is this supposed to be magnified?
That's what we want to get.
Yeah, I got
Maybe 10.
because we just, there's more moles.
5 to 6 years ago.
Bid the same
You have 1,044.
Oh, but keeping in mind that
Is your calculator?
order of operation without, unless you come parentheses around, right? So, okay, I think I checked.
You didn't check us.
I'm almost ready to set my lights up and then I'll have to do okay, what are we getting over here? Okay, I checked everybody off. Any questions? Homework tonight is one page, pretty simple. The first few are just identify if it's positive or negative. The next 3 are doing this equation. So it should be pretty quick to get done. So, which you should have time after I pass back. You can decide if you want to work on test corrections right now or work on the homework. But before you do that, pause what you're doing, everybody. I just want to address a few things about the test and then I'll pass it back to you. Or we'll give your multiple choice back.
Oh no.
Okay, so overall, I was very pleased with what I saw on this test. And let me pull up our data here. Because once again, I know it's hard to remember because like you've been in school for like so many years and been trained a certain way. But percentages mean different things in this class than they do in other classes. Okay, so this right here is where our graph went after Unit 8. Okay, so this final spot right here, you guys are the orange one, is where you guys average ended for Unit 8. Which to me was super exciting because as I mentioned at the beginning unit, this is a unit I've been trying to revamp and change and make better in how I teach it. Because this is where students were last year. And these students still passed the AP test. But it was like the lowest of all of them. Okay, so keep in mind, this graph shows the blue line is those that passed with a 3, their average score. The red dashed line is those that passed with a 4 last year. And then the yellow is those that passed with a 5. So you guys as an average, I was so excited because we had major improvement from last year as a class in the overall. So I understand once again, your average as a class was a 62%, which I get is like not optimum of what you would think, but in this class, a 62 means you passed the AP exam.
Let's go.
Which is all we care about. Okay? So keep in mind, you guys are doing better than you maybe think you are. Now, with that being said, as you know, we don't leave those mistakes. We want to still learn from them, so we fill in the holes. So what I decided, because we do have a little bit of overlap with correcting this test and being in Unit 9 at the same time and the Unit 9 test. So the deadline for the test corrections for this test are March 26th, which is not next week, but the following Tuesday. So you have a little less than 2 weeks from today to get test corrections in. Not counting today, you have 4 opportunities to meet with me, because we'll have 4 classes between then and the deadline. Because of the overlap, though, I did make an executive decision that for the FRQ portion of the test, if you want to get your points back, you can just correct it, and there is no retake.
Sick.
The multiple choice will have a retake if you want your points back. But to simplify it a little bit, you only have to correct the FRQ. Does that make sense, everybody? Okay, any questions there?
Yeah.
Okay, find your, so you should still have your multiple choice test packet. Pull that out and I'm going to give you the correct answers.
Sick.
So pull out your multiple choice packet for Unit 8, and I'm going to give you the right answers, everybody. So,
You don't need to.
after, if you need it, yes. Like, did you not circle any in there? Okay.
You just got 100%.
Go through and highlight the right answers still, but then if you need your bubble sheet, I'll give it back to you. Oh, I guess I can stop recording now.